Thanks very much, Erica. Welcome everybody to this science session for calibration, validation, and product assessment. So Erica already introduced myself and Marwan, that I wish to thank for accepting to co-chair this session. We have 5 presentations today. The first one will be given by Peter Minnett from the University of Miami. Peter, floor is yours.
Thank you very much, Daniel. Okay, it gives me great pleasure to be able to talk about MODIS to such a distinguished group. And I would like, first of all, to invite you to come with me in a time warp. I don't think anybody will get hurt, but we're going back in time to the mid-1990s. Now, 2 people, Neville Smith and Michel Lefebvre, were developing the idea of a global ocean data assimilation experiment, and it became known as GODET. I will use this. And the idea was to conduct a 10-year international demonstration of the feasibility and utility of using real-time global ocean forecasting. And of course, satellite-derived SST was a major component of this. At this time, there were many groups around the world producing something they called SST, using different algorithms applied to different satellite instruments. And it wasn't at all clear that these SST fields were very meaningful and how much they had in common. And this led to the development of the GRIST, the Group for High Resolution Sea Surface Temperature pilot project under the leadership of Craig Donlan. Going back, further in time to the 1980s, NASA was developing the idea of the Earth observing system, which was going to consist of many satellites, including 3 that would be put into sun-synchronous polar orbits. These became known as Terra, Aqua, and Aura. Terra and Aqua were focusing mostly on the oceans and the land and the atmosphere. Aura was mostly just atmosphere. There needed to be significant developments in the ground segments at this time. I remember it well. When you wanted satellite data, you got in touch with the receiving station, put in an order, and they mailed you a box of 9-track tapes, which would arrive a few weeks later. This wasn't a very feasible solution to the ambitions of the Earth observing system. And so a good deal of effort went into improving ground stations and communication links and data distribution. So we have commonality. The Earth observing system and GRIST have common foci, common objectives, and a common history. The first of the Earth observing polar orbiters was Terra, and it was launched in the closing days of 1999. There was a lot of political pressure to launch before the year 2000. It was already many, many years behind schedule. Those of you who remember the year 2000 will remember the Y2K bug, which caused a great deal of concern because most computer operating systems only had 2 digits for the year. And so there was a concern that on the 1st of January, year 2000, some computers would think it was the 1st of January, the year 1900. And so even though the launch was very successful, the satellite and the instruments were not powered up and tested until January to make sure there was no Y2K issue. Aqua was launched a few years later, and the lifetimes of these satellites were planned to be 5 and 6 years. That was thought to be pretty ambitious at the time. Now we're past 20 years for both of them, and that is a great testament to the skills of the scientists and engineers and technicians involved in keeping these instruments on these satellites alive. Terra was put into a 10:30 morning orbit There was belief at that time over the oceans that it was a cloud minimum. Turned out it's not really very much of a minimum. And Aqua was put into the 1330 afternoon orbit and became one of a number of satellites that constituted the A train. Each satellite had multiple sensors on them. Most of them were brand new, never been flown before, including MODIS, the Moderate Resolution Imaging Spectroradiometer, which flew on both satellites and continues to fly today. And as of 3 hours ago, both were in nominal operational status. So, MODIS is a big instrument. The satellites are big as well. And the cutaway diagram here shows the internal array of some of the critical components. A remarkable characteristic was this large paddle wheel scan mirror, which has two sides. This means it can rotate quite slowly compared to previous mirrors, such as on AVHRR. Down here is a large aperture going down to the Earth view. The infrared calibration was through a space view of cold space and this rather novel grooved black body. There was concern about how well this would perform, and it turned out it was really, really good. And it has a number, I think 7 thermistors embedded in it. MODIS had many, many innovations. And in the early months of the Terra mission, we realized that innovation means problems. When I was at Goddard, having lunch with a friend of mine, also working on MODIS, he said, it's a shame we should never get involved with a mission that rhymes with error. And he was right. There were many problems. Some of these came from the fact that there were 36 spectral bands. AVHRR, you remember, had 5. The spatial resolution went from 250 meters in some of the visible channels to 1 kilometer at nadir for the infrared and other visible channels. There were multiple detectors for each spectral band, 40 for the high resolution bands and 10 for the 1 kilometer bands. These were mounted on 4 separate focal plane arrays. Again, another innovation. And the 2-sided paddle wheel scan mirror was very innovative and very problematic. The groove body turned out to be very good. And here is a list of the visible spectral bands and the infrared spectral bands. What is important for this group is that there was the traditional split window bands at 11 and 12 microns. Unlike all of the previous infrared radiometers that have flown, and I think most of those that have flown subsequently, these are actually very narrow bands. Their bandwidth is 0.5 micron. The standard bandwidth on other radiometers is 1 micron. An innovation was to have another split window in the mid-infrared atmospheric transmission window at about 4 microns. This had not been flown before. So why do that? Well, if we look at the calculated atmospheric transmission spectra for different atmosphere, which characterize the atmospheres from tropical to polar, we see in this elbow here, there's relatively little change in the atmospheric transmission around the globe compared to what we see at the usual split window channel here. Therefore, measurements taken in these bands, shown as green and blue, should be less sensitive to variations in the atmospheric properties, specifically water vapor. This shows the Planckian emission at temperatures going from 0 to 30 degrees C, and the usual split window channels are positioned close to the peak of Planck's function, which is great. These are not. But however, if you look, the change in the signal going from 0 to 30 is proportionally much larger than going from 0 to 30 there. So there is a radiometric advantage in those channels as well. These are diagrams of the focal plane arrays. They're not side by side. They're positioned in the sensor to be optimized. And the little crosses here are the optical axes of the instrument. So very few of the detectors are even close to the optical axis. This leads to a risk of optical crosstalk, which was in fact found. These are chilled. The mercury cadmium telluride detectors, the silicon detectors are just running at the ambient temperature of the spacecraft. Now, this is one of my favorite pictures. It looks like a genie trying to escape from a magic bottle. It is, in fact, a reflection of a technician in the one side of the paddle wheel. In the clean room, he's holding the motor. So this is one side of a mirror, which is made of beryllium, plated in nickel, and coated in silver, and finished with a protective layer. It has to be optically flat, and both sides have to be parallel and also optically flat. The protective coating was put on to benefit the visible channels. It introduced some very serious issues in the infrared. More about that later. The rotation speed is very slow compared to previous and subsequent scan mirrors on other radiometers. And that, I think, contributes to the fact each of these has been running essentially without break for over 20 years. This is the plane of the one surface of the scan mirror. And this is just normal to it. And the scan mirror, the incident angle on the scan mirror of emission from the Earth view at nadir is at 38 degrees to normal. The start of the scan of the Earth view starts at 10 degrees, ends at 65 degrees. The problem, or one of the problems, is that when you look at space and the black body, you're not looking at angles that include the Earth view. If there's any angular dependence on the properties of the mirror, that is an issue. And it turned out, because of this multi-layer coating, that this was the case. This is just the same information, but considering a 360-degree rotation. So this Earth scan begins here, goes through nadir, and stops there. The onboard black body is here, and the space view is there. However, all of these problems, and I'm only mentioning a few, were overcome. And so this is an image of the Gulf Stream. I'm sure you'll recognize it. And the gray up here is the effect of clouds. This is an image taken from May 8th, 2000, year 2000, only a few months after the instrument was switched on. And the SSTs are very, very clean. Now, to get to the position where we can derive SSTs, we have to be sure we're not trying to get an SST through a cloud, because this is not possible, as you all know. To begin with, we use just a binary decision tree cloud mask, which we developed for AVHRR and then just transported it to MODIS. And this is a sequence of tests, spectral tests, spatial variability tests, and so on. And for a pixel to be classified as cloud-free, it has to pass every test. And we realized very early on that there were areas where there was clearly too much cloud identified. This led to a development of a machine learning approach, which we call the alternating decision trees, where a similar set of tests are applied to the pixels and their surrounding pixels. But the thresholds are determined by a machine learning approach, and the actual tests are determined by a machine learning approach. And the data that was used to train these consisted of hundreds of thousands of matchups between the brightness temperatures and in situ measurements, mostly from the IQAM drifting buoy array. So that did introduce improvements over here: binary tree, alternating decision tree. The other benefit of the alternating decision tree is that a pixel or a group of pixels can fail one test, but if that test is not weighted very highly, it still leads to a cloud-free cluster of pixels being determined. And it shows that here in the Southern Ocean, and this is in June, so this is the Southern Ocean winter, we get much more coverage. And another example is the Mediterranean, which had lots of gaps before and is largely filled in. So now we've got clusters of cloud-free pixels. How do we derive the SST? Well, we took over the NLSST that had been developed for AVHRR by Charlie Walton in the 1990s, and we added 3 extra terms which are particular to MODIS. This is the so-called NLSST algorithm. These are the brightness temperatures at channels 31 and 32, which are about 11 and 12 microns wavelength. Sec and theta. Theta is the satellite zenith angle at the Earth's surface. This term, which goes back to the NLSST, is a first guess estimate, and that people find, myself including, not very satisfactory, because it implies you need to know what the answer is before you can derive it. However, you can tolerate quite large errors, or uncertainties, I should say, in the T surface without compromising the derived SST. During the night, we use this derived SST, referred to as SST4 as the first guess. And because it's at 4 microns, it can't be used during the day. And during the day, we take the SST surface as the value from the Canadian Meteorological Center field. The coefficients for the algorithms are derived by analysis of now millions of matchups between the satellite brightness temperature measurements and the in situ measurements. And so there are 84 sets of coefficients for each satellite instrument. And they're derived in monthly groups, months of the year, and 7 latitude bands. And here we have a comparison as monthly box plots of the SST derived from Terra. So this is 2000, this is 2022, I think. This is the latitude band south of 40 degrees south, 40 degrees to 20 degrees south, 20 to the equator, equator to 20 degrees north, and so on. And this is north of 60 degrees. There is remarkable consistency throughout the 2 missions. The red line is at minus 0.17 degrees, which is the global, or the estimate of the global value for the mean skin effect. The skin being where the infrared radiation is emitted is about 0.17 degrees colder on average than a subsurface temperature. And again, remarkable consistency. This is the SST4. These are both nighttime retrievals, and we see, as intended, the SST4 is more accurate. So these are against the IQAM drifters. So if we presume that the IQAM drifters are producing a good representation of the global sea surface temperature at a depth of 20 centimeters, so we can argue that MODIS is producing a very good representation of the skin temperature of the ocean over 2 decades for each sensor. Now, there is variability in the skin to subsurface temperature, and this is shown here. If we had enough ships, we could with radiometers, we could replace the buoys with radiometric measurements, but we don't. So we have to somehow take this into account. This is the wind speed dependence of the skin temperature minus the subskin temperature, or a temperature lower down from various papers. And the one labeled data is in fact from Chong Jia's sail drone skin SST retrievals. And the remarkable thing is that at higher wind speeds, the asymptote here of all of these separate data sets taken by separate people on separate ships using separate instruments are within 20 millikelvins at the asymptote. So there is something physical going on here. At low wind speeds, this tight relationship breaks down, and there are a number of reasons why that should be so. So how do we get those measurements? We use an instrument called the MARY, which is a Fourier transform radiometer, using 2 internal black bodies for calibration at sea. Calibration is done before and after every measurement cycle, so that's every few minutes at sea. And before and after going to sea, they're tested in the laboratory against a NIST-designed black body, and periodically these are compared at NIST or NPL against standard black bodies and standard radiometers. They now run autonomously. And up until COVID, we had 3 running continuously on cruise ships and 1 on a range of research vessels, most recently the Ron Brown of NOAA. And SST skin is derived from measurements at wavelengths of 7.7 microns, and I can discuss that offline if you're interested. So this is the skin temperature derived from the MARY, from the Ronald Brown. From December 1990 to February 2020. So this is pre-COVID. This is pre-COVID. The ship was in Cape Town when travel restrictions began to be implemented because of the pandemic, and it set off to come slowly back to the US to Norfolk, Virginia, where it stayed tied up for over 6 months, just idled. Then NOAA decided they had to continue their scientific program, and it began sailing again. This is the collection of cruise tracks from the MARY, from the Ron Brown in 2021, 22, and 23. And about 1 year ago, it ended up here in Mississippi for a major midlife refit, and it's expected to come back into service later this year. So it's a gap of about 16 to 18 months. The Royal Caribbean cruise ships were all voluntarily idled when the pandemic hit and there were travel restrictions. But once travel could be continued, they resumed, and we began to refurbish our equipment on the Celebrity Equinox. And the data began to flow again in August of 19 last year. This is the Equinox. It's a big ship, and that is the MARY. That's a better view of the MARY. And this is how it looked after it'd been refurbished and everything was running again. These are the cruise tracks around the Caribbean of the skin SST from the Equinox. at the end of 2023 and up to April 2024. The ship is now in the Mediterranean and we're getting data transmitted back home. How good are these? Well, these are the comparisons with the Mary and the MODIS SSTs. Our 2019 just refers to when there was the last global reprocessing of the data set by NASA. The remote standard deviations here for the SST at night are very good. The median biases for quality 0 are very good. Quality 1 means you can use it, but it's going through a much longer atmospheric path length. And for SST4, robust standard deviations are even better. Throughout most of their lifetime, the satellites have been in a maintained orbit. That means every 16 days they repeat exactly the track that they flew before. And that requires quite frequent orbital adjustments. And eventually the propellants on board, remembering these are 5- and 6-year lifetimes, ran out and the satellites have been allowed to drift. So Terra is drifting earlier in the day. Now it's about 9:15 or 9:40 maybe. Aqua is drifting later in the afternoon. So to summarize, throughout the period of GRIST, MODIS has been, the two MODISes have been providing very good, very accurate, very stable SSTs. There have been several sets of algorithm improvements, and the last complete reprocessing was done in 2019, and we anticipate that NASA will do a total reprocessing when the instruments are eventually passivated, I think is the term. It means switched off. The SST fields are consistent, and they have demonstrated accuracy, which is useful for many scientific applications. The satellites have been in maintained orbits, as I just mentioned. Now they're drifting. And the data at L2P, L3, and L4 as part of MUIR are all available from the PODAC, and they consist of some of the most downloaded files from the PODAC. There have been lots of people involved over these 20 years, and lots of contributions primarily from NASA. Both the physical oceanography program at the outset, now what's called the Senior Review program. The Ocean Biology Processing Group took over most of the processing quite early in the program. We were lucky to get access to the supercomputers at NOAA's North Carolina Cooperative Institute for Climate and Satellites, which is where we do a lot of the algorithm development. And the PODAC does the distribution, as well as generating L2P. We couldn't have done this without Royal Caribbean or support from many research vessels, especially the Ron Brown. Thank you.
Thank you very much, Peter. So time for questions. We can start from people online if there are any questions. Just a kind reminder every time to introduce yourself and your institution. So we have a first question from Swadhin Satapathy. Please go ahead.
Hello. Hi. Can you hear me? Yeah. So thanks, Peter, for the nice talk. I just needed to ask that you showed a comparison between the night MODIS SST skin versus the subsurface temperature from ICOM drifters. So there was this ±1 Kelvin that got scared. So is it due to the difference in the depth of measurement, or are there any other factors that is playing a role here?
It's not plus minus, it is minus. The skin is nearly always colder than the ocean at a depth of just a few millimeters and below, because the ocean is nearly always giving up heat to the atmosphere, and that requires there to be a cooler skin than beneath. And I showed the wind speed dependence from a number of papers. There are a lot more that we need to be able to do. And a number of people have said, well, why don't we do better? Well, to do better, in the first instance, we need a wind speed to apply those parameterizations that I showed. We need a wind speed at 1 kilometer resolution within, say, 30 minutes of the satellite overpass. If anybody can give me that, I'll use it. The other factors, of course, are the net radiative balance. May not be a balance, it might be changing. But in the infrared, the skin layer is absorbing emission from the atmosphere and the sun, as well as re-emitting it back. Turbulent heat fluxes are going to alter the size of the temperature drop across the skin layer, etc. But in order to incorporate that variability into an algorithm that does the retrieval on a pixel by pixel basis, we need information which is just not available. Okay?
Yeah, okay, yeah. Thanks for that.
I don't see presently questions online, so there's a question.
Ed, don't you dare.
Marwan?
Hi, Peter. Thanks for your talk. Quick question with respect to the use of several SST coefficients depending on the latitude. So recently with Stéphane Sopicard, we generated a climatology of SST maximum gradients using almost the entire Aqua Modis mission. And we noticed that there's kind of a signature. We see like a large scale. We see large scale horizontal stripes in the level 3 maps of climatologies, which surely is going to affect applications like the use of these climatologies for reducing the misclassification of ocean fronts as clouds. So I was wondering if you have observed that in the data, and
no,
if
we haven't.
If so,
where do these stripes occur?
Well, I would assume that they are pretty much they coincide with the division of the latitudes that are used for the different SST coefficients. I can share an image in the chat, maybe.
Why don't you just email it to me and I'll look at it?
Sure.
But I should add that there isn't an abrupt change from this latitude band to that latitude band. There's a ramp which extends over 10 degrees of latitude. So in fact, there should be a near continuous change in the atmospheric direction. The latitude bands are simply there to determine the matchups to be used to produce the coefficients. Now, many years ago, when machine learning was a new thing, a colleague of mine in the computer engineering department was very keen on that. And he asked me if I could produce some data for his graduate students or postdoc. And so I said, well, why don't you look at these matchups, a few million matchups, and see what your machine learning algorithm can produce for boundaries between the atmospheric properties, zonal boundaries around the globe. And they came up almost exactly at these 20-degree intervals. And that is just because of the large-scale atmospheric circulation. We then asked this student to do not just zonal, but longitudinally varying boundaries as well, which she did. And this was really very interesting. And we put in 4 proposals, 2 to NASA, 2 to NSF, and none of them were funded. Now, of course, you look at the announcements, machine learning is all over the place, but this was about 15 years ago. So I understand what you're saying, Marwan, but I don't see that the boundaries are likely to be caused by the change in the coefficients because we have the ramps. And of course, the atmosphere is zonal.
We don't really see them in the synoptic data anyways. They are very discrete even in the climatology of 20 years. So,
okay, all right. If you send that to me, I'll have a look into it.
thanks, Peter.
Thanks, Marwan. I see another question from Mike Chin online.
Don't forget about the audience here.
Or I can't see Mike speaking. So Ed, please go ahead.
Can I go ahead? Okay, so Ed Armstrong from the JPL PODAC. Thank you, Peter, for that. Yeah, that beautiful, wonderful history of these two beautiful instruments. So yeah, my question is on the machine learning approach for the alternating decision tree. I'm just kind of curious how you do the weighting. So if you have a machine learning that is you know, a test that's on the variance, say you're training on variance versus like a threshold, how do you like weight those two? When does like one become more important than the other? There's got to be some logic behind that.
You let the algorithm determine that. You say, these are the inputs that you've got. Tell me how you want to use them. And it comes back with a series of tests and a series of weights that should be applied to the results of those tests.
I see. So the algorithm tells you what the weights are at the end of the day.
Yeah. And then when the benefit of this approach, rather than the binary decision tree where it has to be, everything has to be positive to pass. You can accept negative results as long as they're not very important. And at the end, you get a number which determines the confidence of the cloud screening.
Is that number reported anywhere in the processing chain?
I don't know. I suspect not.
Might be good to add for the reprocessing campaign to report.
Yeah, okay,
that's an algorithm lineage.
That is a really good suggestion, Ed. I'll look into that.
Thank you.
Please go ahead. Yes, Mike?
Yeah, hello. Sorry, yeah. I couldn't unmute myself. Just like a follow-up of the the latitude dependence. I did see that crease in the modus result, and it seems like it's coming from the SSES bias field. So have you just take a Marwan? Are you still there? If you can hear me, did you try to differentiate between the skin temperature and then SSES bias term? That's where I saw it.
So just to clarify, where we have seen these bands, they are present in the climatology of SST maximum gradients. We haven't conducted any kind of statistical analysis.
Oh, okay, so not in the field itself.
Yeah, it would be very difficult, I would assume, to see that in the fields.
Yeah.
Thanks for that clarification.
Right. That's all for me. Thank you.
We have another question here in the room.
Irina Gladko, representing now. I have first of all, thank you very much for the good historical overview. I really appreciate it. I've learned a lot today. I have a quick question. So you have a separate coefficients for latitudes and also for the time of the year. Have you ever plotted them to see that maybe it could be modeled directly into the equation rather than, you know, discretized in different bins and fit it separately? Because it might be just some kind of a functional dependence and you are just looking at discrete representation of it.
Yeah, we have done that in this pilot study that I mentioned about machine learning approaches. And when we looked at the boundaries the student produced, they more or less coincided with the gyres, upwelling regions, and so on. So there were physical bases for this. And building on that rather superficial result was part of our proposals that were never funded.
I see. So you don't really know whether there is some latitudinal dependence, or maybe latitude is some variable that represents something else going on that could be included in the model.
It could well be.
Yeah. Okay.
The latitudinal dependence is taken care of. What we were looking for was the longitudinal dependence. And for instance, SE temperature differences influence the accuracy of the retrievals, but we don't have enough information to incorporate that in the algorithm.
I see. All right.
But it regionally might well work, but that'll be somebody else's task, I think.
Yeah, and just an extra comment, if your machine learning proposals, 4 of them were not funded 15 years ago, you should have reapplied, 5 years later, and you would have get it funded, I guess.
I dare say that is true, but my colleague has moved on. In fact, he's retired. So the people in his department are not interested in this anymore. They're much more interested in new new types of machine learning approaches. And that was one of the criticisms of the proposals. It said, you're not doing anything new in the machine learning sphere. And our response was, no, that's not what we want. We want to do something new in the applications of machine learning. And it fell between 2 stools, between both NASA and NSF, and neither organization will admit this is possible. But the oceanography people said, ooh, we don't really know what's going on here, so how do we decide? We'll ask the machine learning teams. The machine learning team said, well, this is okay, but it's not new.
From their perspective.
Yeah.
Oh, okay. All right. Well, thank you.
Thank you.
Any more questions for Peter? Yes, Andy.
Andy Harris, University of Maryland. First time I think I've said that. 2 questions. One is obviously there is a striping thing and has been for a long time, and I know Maroon worked on it. Are sort of improved destriped level 1 data available somewhere, or is it something that anybody who wants to deal with it is going to have to address that themselves?
What do you mean by the destriping thing?
Well, Maroon can probably answer that better than I can.
But, okay, it's detector striping.
Yes.
Yeah, okay. Talk to Jack Zhong at NASA Goddard.
Okay, so that you're saying I should talk to him, or are you saying that, yes, the product does exist? Or
by the time we get it, those have been removed.
Okay, right. The second thing is just vaguely occurred to me when you showed the orbit drifts. Was there ever some sort of campaign to maybe just use a little bit of fuel to try and improve the trajectory, or did it just said, oh, we've run out of fuel, let's let it drift? No. Because they could have probably just given it a little kick to make it, kind of go earlier, then later, and it would have stayed close to the nominal time for a lot longer.
They did as much as they could with the fuel on board. Remember, these spacecrafts were fueled for 5 and 6 years. Yeah. And getting to this point is remarkable. Right. But no, they have no propellant left. I think they have just enough to have a controlled re-entry.
Right.
The spacecraft will be deactivated when the angle of the solar panels to the incoming solar radiation is such
you don't get any power.
They can't generate enough power to keep them alive.
Okay.
I guess we need to move on to the next speaker. Thanks very much, Peter.
Thank you.
So our next speaker is Anna Carroll from EUMETSAT.
Okay, hi everybody. So I'm going to give an update on fiducial reference measurements for SST and CIs. So this is an overview of activities at EUMETSAT, funded by Copernicus, and I'll include the activities of the Trusted Project, and there are many kind of partner organisations with that. They're all listed there below. So I'll start and I'll go through fiducial reference measurements for sea surface temperature, talk about the need for them, our reference SST from SLSTR, and go through some of the activities of the Trusted Project. And then in the second part of the talk, I'll talk about fiducial reference measurements for sea ice surface temperature. Steiner gave a little bit of an overview earlier today. So reference data, in situ data, are essential for sea surface temperature validation. They've been used for many years from GRIST. So this includes radiometers, drifting buoys, more buoys than Argo. So co-locations with all the reference data are important for satellite validation. And also intercomparisons with other satellite sea surface temperature. But for climate quality and reference satellite SSTs, such as from Sentinel-3 SLSTR, we also need to do co-locations with fiducial reference measurements. So this includes both the radiometers, such as those that Peter has just explained and that Fred explained earlier in the week, but also fiducial reference measurements from drifting buoys, such as from the Trusted Project. So SLSTR provides reference sea surface temperature for both sea surface temperature, and we're working towards reference sea ice surface temperature products, as Gary explained earlier today. So these are critical reference sea surface temperature data for operational weather forecasting and ocean forecasting and climate monitoring. And the significance of these data is increasing as the climate situation amplifies. And therefore, we need high quality fiducial reference measurements for validation. And these are critical to ensure satellite SST data quality, uncertainties, and stabilities. So a little bit now on the definition of fiducial reference measurements. Climate quality and operational reference satellite sea surface temperature requires a subset of extremely high quality fiducial reference measurements. This means that we have traceability for climate data records so that we can understand how accurate the products really are and to deliver the required confidence. It includes a long-term investment. So this is balanced to deliver a satellite mission with a known product quality that is fit for purpose. And once we're doing these activities, the global coordination means that we have increased quality in the whole network. So this is beneficial for both satellite and ground-based users. So fiducial reference measurements for sea surface temperature, this led us to the Trusted Project, where we're focusing on the FRM for drifting buoys. So the radiometers are covered by the ships for SST activities that Fred described and that Peter had just described, and we're really focusing on fiducial reference measurements from drifting buoys. So the Trusted Project began in 2018, and this was really to establish a sustainable FRM for satellite SST and later IST as well. So far we've deployed over 187 SVP BRST high resolution drifters. And I'll come to the description of the buoys in a minute, but they have both high resolution TRST sensors and the traditional SST sensors. But what's different about these buoys? They have a calibration per sensor, metadata access, storage and QC, and we do stability analyses. And if we can recover the buoys afterwards, then we try to do that as well for limited numbers. There's been a lot of work recently on traceability diagrams and the metrology, particularly the coordination with the European Metrology Network. For the deployments, we've had recent focus on high latitude deployments and in the Baltic, Mediterranean seas, as well as global. And the development for the IST buoys started in 2022. So for the trusted buoys, this is based on the WMO DBCP standard, so the SVP, but the trusted ones are called the BRST design. But it's basically the same, but it has an additional detachable kind of sensor module, which includes both a high resolution SST sensor, so HRSST2, but in the trusted project, we're defining this as a TRST, plus a hydrostatic pressure sensor for looking at the depth of the buoy. If you want some more technical specifications, you can go to those links. So for the recent and planned deployments, we've had quite a few recent deployments, and the deployments in June this year, we have some in the Indian Ocean, the Arctic and the South Atlantic. We still have some kind of gaps in the global areas, and we'll be looking at these in the next year or two. There's been a lot of work in the last year on the development of traceability trees and uncertainty diagrams. So these are kind of following the same analysis and thoughts along the for the paper that Fred produced for the radiometers, for example. And Mark Leman is writing something up in preparation for that for traceability diagrams for the buoys. So the aim is for an uncertainty model per buoy with specifically defined measurands. And this means it's for the drifting buoy SST at a particular depth of sensor and at a particular measurement time. So we're coordinating with the European Metrology Network to bring in their expertise whilst we produce these traceability diagrams. And these activities are critical to ensure Fiducial reference measurement standard is met. One aspect still to do is thinking about the uncertainty diagrams for the validation part, so the skin to depth adjustments and the validation models. Another aspect we've been working on in the last year or two is quality control and metadata for FRM. So this is together with the WMO Ocean Ops, or JCOM Ops, as it used to be called, as Gary was talking about earlier in the week. So this means having machine searchable and accessible global measurement metadata. It means having specification of the full QC procedure and definition for the route to FRM. And it means having quality control data propagated through the full data acquisition and processing steps and is easily available to users. So all of these aspects are currently in progress. So validation using trusted drifters for SLSTR SST. This is ongoing. So we use the SLSTR matchup database. It's available on request if you're interested. So the utilization of the full metadata and QC is in progress. We're waiting for the Ocean Ops web pages to come back online, and then that work will be done later this year. Considerations of the validation methodology in progress. So things we're thinking about are whether to use the traditional drifting buoy validation methods or to treat trusted in a similar way to the GTMBA, and shipborne radiometers for looking at long-term stability analyses. So we're still thinking about that one. But this kind of aspect would have impacts on the deployment planning to ensure the longest lifetime possible for each buoy for the stability analyses. I just wanted to come back a little bit to the definitions. If you recall Gary's presentation on the HRST testing from earlier in the week, so you'll remember the definitions for the HRSST2 drifters. This is what's available from the Global Drifter Program, for example, and what was agreed by the DBCP GRISP pilot project over 10 years ago now. So what we have for FRM is based on the HRSST2, but is a subset of that with additional specifications. For the HRSST2, this includes the global metadata information, but the FRM for drifters, for such as trusted, so this follows the HRSST2 specification, plus we have a few other aspects, and this includes the calibration per sensor in a laboratory, independent of sensor manufacture, the definition of the uncertainty budget and traceability diagram, as I explained, the measurement metadata and improved quality control, the coordination with the national metrology institutes and the European Metrology Network, and if we can, then post-deployment calibration and analysis where there's the opportunity. So all of these definitions have been coordinated with the DBCP and presented at recent meetings. Okay, so now we'll move on to sea ice surface temperature. So IST is classified as an essential climate variable with requirements of 1K total uncertainty, and poor coverage of IST in situ observations in the high latitudes limits the satellite IST algorithm development and validation. Since we have developments towards reference dual view SLSTR IST, such as was described by Gary this morning, we now have the pre-operational data stream available for that. But that also means that we need to have an IST FRM data available for validation. I think one of the kind of interesting things that we've found by looking at some of the pre-operational IST data as well initially is how much variability there is day to day. So it's very unlike validating a sea surface temperature field, for example. So this is even more critical why we need the high quality FRM in situ data. So within the Trusted project, we've begun to develop the IST FRM buoys. This is the what Steiner was describing earlier. We began on the requirements. They're now available from that link from the EUMETSAT website if you're interested. So last year we focused on the IST sensor design and prototype. So you can see the probe there. It was also in Steiner's photographs. This year we're focusing on the buoy prototype, testing and calibration activities. So in the end, I think we'll probably end up with a kind of an SVP kind of type of buoy with the probe attached. And then the aim is then to do in 2025 further testing and calibration with operational deployments beginning in 26 to 27. So yeah, so that's answering Sandra's question earlier. I think what we'd be interested in hearing from you would be, yeah, the number of kind of instruments that would be needed, regions that they should be deployed in, any other requests. We'll be starting to do the planning for the next phase of the project later this year, so it would be good to gather any requests and needs now. Okay, so just to summarize, continuation of FRM is crucial for underpinning climate and reference satellite SST data quality, validating the uncertainties and assessing long-term stabilities for climate data records. Activities on developing FRM for sea ice surface temperature is critical to continue for validating the new era of highest quality dual view satellite sea ice surface temperature products, for example, from SLSTR. In the Trusted project, we've so far deployed over 187 SST drifters since 2019, and we're currently testing and calibrating the IST prototype buoy. A couple of considerations. Further work is needed on documenting the traceability trees and uncertainty diagrams for the validation methodology, such as the conversion of skin to depth SST. And also considerations are needed on validation methodology for Trusted, such as traditional methods or those used for GT-MBA stability analyses. Here's just a further acknowledgements, and there's a couple of publications there if you're interested. Thank you.
Thank you very much. And I think we have time for a couple of questions. I can't see questions online, so we have a question here in the room.
Thanks for the talk. Peter Galbraith, Fisheries and Oceans Canada. Of all the buoys that have been deployed since 2019, what's the life cycle? How long do they last? That's my first question. And second question would be, considering there's about 3,000 Argo floats on a 10-day cycle means every day there's like 300 surface dots, right? Where you could get, so are those used?
Yeah, so for the first question, the lifetime really depends on where we deploy them. So typically for the trusted buoys, the lifetime's been lower than for other DBCP buoys because we've been having some deployments in areas like the Baltic or higher latitudes. But typically we could get maybe a year and a half deployment length for those. I think for the next phase, we'll try to be deploying them in areas where we can get a longer lifetime. For the second question, yes, we use Argo for our satellite validation. Yeah.
Okay, thank you.
I guess I saw Marwan hand raised.
Yes, Haifang's got his hand up.
No? So
go ahead,
Haifeng,
Daniel.
please go ahead.
I thought someone online. Haifeng from Bureau of Meteorology. Nice talk, Anne. I was wondering, so from Gary's talk yesterday, we know that the HRSST2 is kind of the standard for the drifting buoys now. I was wondering, in addition to the extra sensor, the trusted buoys is like the next step or next standard, or is it just a project and it might not be the standard for all the buoys in the future?
Yeah, I mean, it's a project, so it's a subset of buoys for FRM. So it's got that specific purpose, but it's based on the HRSST2 initially, but then with extra specifications to meet the FRM standards. So, but as Gary said the other day, yeah, all the HRSST2 buoys are really important and we use them. But we need these kind of subset of FRM buoys to do the extra work for the climate reference SLST RSST validation.
Any more questions? Thank you very much. And